These are the notes for AP Calculus on the topic of applied problems using tables of data. So this table below shows the differentiable function. Remember, differentiable means you can take the derivative anywhere. It has a derivative, v of t, representing the velocity of a car. So you can see in the first row we're given the velocity of the car, v of t, and the units are meters per second. And the second row we're given the time in seconds. So it's telling us at specific times what's the velocity of the car. It says use the data in the table to estimate the acceleration of the car at t equals 5. So it says estimate because normally to get acceleration, we would take the derivative of velocity. But the trouble is we don't have the equation for velocity here. We only have a table of values. So the best we can do is to estimate. We can't get it exactly. And it asks us to show the computations that lead to our answer and indicate units of measure. All right, so let's look at the table at the time row, which is the second row, from where time 5 is. Well, let's see, time 5 is right here between 4 and 6. So the best we can do, since we can't actually take the derivative and figure out the exact acceleration, is to remember another word for the derivative is the slope. So use the slope of the points closest to t equals 5. In this case, that would be these 2 points right there. So we can say a of 5, acceleration time, which is the same as v prime of 5, derivative velocity, is approximately equal to v of 6 minus the velocity times 4 over 6 minus 4, just our slope formula. The velocity at time 6 is 25, you can clear the table. The velocity at time 4 is 16 over 6 minus 4. Gives you 25 minus 16 is 9 over 2. Okay, so to show the computations that lead to your answer, you can either show this or this expression or both to show where you got it from. And then 9 over 2 is your answer and indicate units of measure. Well, anytime you want the units, just look at the units right here on your fractional expression. The units for velocity are meters per second. The units for time are seconds, so it's meters per second, which you write as meters per second squared. Now, the next one says, same thing, use the data table to estimate the acceleration of the car, this time at time 14. 14, if we look, is right here on the table. So at 14, there's actually 3 ways you can do that. You can use the points on either side of 14, which I'm going to use right here, 12 and 16, or you could use 12 and 14 or 14 and 16. Any of those would be considered a legitimate estimates of the acceleration because we don't necessarily know which of those is going to be closest to the exact acceleration at time 14. We're just estimating. And those would be the 3 points closest to it. So, we need 3 of those. You don't have to do all 3. So I'm going to say that a of 14, which is the same as the derivative of velocity of 14, is approximately equal to, if I use these 2 points on either side of 14, that'd be v of 16 minus v of 12 over 16 minus 12. Velocity times 16 is 14, minus the velocity times 12 is 32, over 16 minus 12. 14 minus 32 is negative 18. 16 minus 12 is 4, so we get negative 9 over 2. This is 2. Again, the units here, units for velocity are meters per second, units for time are seconds, so meters per second is meters per second squared. Then it says calculate the average acceleration of the car over the interval 2 to 16. So average acceleration, remember, doesn't use the acceleration function at all. Here it says calculate, it doesn't say estimate, because we can get this exactly. We take the average acceleration, remember, is the change in velocity over the change in time. The change in velocity would be v of 16 minus v of 2 over the change in time would be 16 minus 2. So if you look, you'll notice this expression looks very similar to the last 2 expressions. Because what we're really doing to estimate the acceleration at one specific time, 5 and 14, is we were just finding the average acceleration over an interval that was really close to the time we're looking for. So v of 16, look in the table, is velocity of 16 is 14, minus v of 2 is 8 over 16 minus 2 is 14. That gives you 6 over 14. Reduces to be 3/7. Again, the units for velocity are meters per second. Units for time or second, so meters per second per second. So meters per second squared. Then from 0 to 16, there's a review one next to here. What's the least number of times when the velocity v of t must equal 10? Justify your answer. Well, remember, the velocity must equal 10 on some interval here. We've got the velocity. We can use possibly the intermediate value theorem. But the one condition of the intermediate value theorem is the function must be continuous on the interval. And notice it tells us, it doesn't say anything about continuity, but it does say it's differentiable. And if it's differentiable, remember, for something to be differentiable, it first has to be continuous for a function to be differentiable. So, when it says it's differentiable, v of t is also continuous. That's implied. It has to be, otherwise it couldn't be differentiable. And when must it equal 10? Well, we want to see, do the y values on either side of each, and we'll have to, there's 10 in between them. So is 10, let's look at our velocity between 0 and 8. No, it is not. Is it between 8 and 16? Yes, it is. So there the velocity would have to equal 10. Is it between 16 and 25? No. 25 to 33? No. Keep looking across. 10 is not between any of the other intervals, so just be one time. So I can say v of t equals 10 at least one time, since, remember to justify using the intermediate value theorem, you can say since v of t is continuous, and we know that since it tells us it's differentiable, and v of interval was 2 to 4, so v of 2, that was the smaller one, that was 8, so that's less than 10, which is less than v of 4. And then just reference the theorem we're using by IVT for intermediate value. Now let's take a look at another example. On this one, you can have all different tables that represent all sorts of things. So your units will be based on the units here. It says the table below shows the differentiable function L of t representing the people waiting in line for Splash Mountain. So notice here, time's on the top row and not on the bottom row. And people, L of t, is what the units for L of t are, people. So use the data in the table to approximate, just another word for estimate, same thing, the rate. Well, rate is another word for the derivative. So we want to approximate the derivative of the number of people waiting in line. Let's change it and t equals 12. So what we're asked to approximate here is the derivative of L of t. So trying to find L prime, in this case specifically at 12. But again, we don't have the equation for L of t, so we can't just take the derivative like we normally would and plug in 12. The best we can do is approximate by looking at our tables. So let's look for where time 12 is. Be careful though, t is 12, and that's not the bottom row like it was on the last problem. Here, time is on the top row, so make sure you look at the top row where you find 12. And 12, you can see, is between 11 and 14, so the closest points we could use, remember the derivative is the slope, to find the slope between the two closest points. So this would be L of 14 minus L of 11 over 14 minus 11. L of 14 is 30, L of 11 is 33, over 14 minus 11. So you get 30 minus 33 is negative 3, over 14 minus 11, 3. Gives you negative 1, and the units for L here are people, so that'd be the units of the numerator, people. The units for time are minutes, so people per minute. So negative means L of t is getting smaller, so there's fewer people waiting in line on average. At time 12, looks like the rate's decreasing before line. Then part B is the same thing. Use the data in the table to approximate the rate at which the number of people is waiting in line. The only difference is a different time. Time 25. So this is L prime of 25. So let's look for time 25 on our table. Notice time is on the top row, 25. In this case, it happens to be there at the very end of our table. So you can't use points on either side of it. The closest points we can use are 25 and the point right before it. So we'll have to use those to do our approximation or estimate. So the L of 25 minus L of 21 over 25 minus 21. L of 25 is 14. L of 21 is 17 over 25 minus 21 gives you 14 minus 17 equals 3 over 25 minus 24. Negative 3/4, and the units for L again are people. Just look at the units of the numerator. Divide by the units for time here are minutes. So people per minute. And finally, it says calculate the average value of L prime of t on the interval 1 to 21. So remember, for average velocity, we didn't use the velocity function. We used the change in position over change in time. For average acceleration, we didn't use the acceleration function of the change in velocity over the change in time. So the average value of L of t is the change in L of t over the change in time. So that would be L of 21 minus L of 1 over 21 minus 1. So L of 21, look at our table, is 17. L of 1 is 8 over 21 minus 1. 17 minus 8 gives you 9 over 21 minus 1 is 20. And the units again, units for L are people. Units for time, minutes. So 9/20, people per minute. And that concludes the notes for AP Calculus on the topic of using tables of data. Applied problems using tables of data.